a chain map tau from C to C prime is called a chain equivalence. It is called a chain equivalence if this class, so we defined homotopy of between two chain maps. When we say that two chain maps are homotopic, right? We defined a relation on the class of chain maps from one chain C to other chain C prime, and we said that uh, tau is related to tau prime is tau is homotopic to tau prime. So this relation was equivalence relation, and then equivalence class we denoted by this. Equivalence class of tau we denoted by this. Uh, so if chain map and we can have a category, right? We can have a category of chains and chain map classes. Okay. Uh, because of the previous result, previous lemma that we proved that composites of chain homotopic chain maps are chain homotopic. So if we use that, then there is a category whose objects. Uh, so here I can write. There is a category. So this is an observation. Observation. There is a category whose objects are chain complexes and whose morphisms are chain homotopy classes. Morphisms are chain homotopy classes. Now, a chain map tau from C to C prime is called a chain equivalence if this its homotopy class, this is an equivalence, right? This is a morphism, right? This is a morphism from C to C prime in this category. If this morphism is an equivalence, if this is an equivalence, in the homotopy category of chain complexes. Now, if there is a chain equivalence from C to C prime, then uh, then uh, we say that C and C prime are chain equivalent. So this was definition of chain equivalence. Next, we have following theorem. If tau prime from C to C prime are chain homotopic, then uh, tau star. So this is a homomorphism induced by tau, and tau prime star from HC to HC prime, they are equal. So these two are equal. Proof. Uh, Assume that D is a homotopy from tau to tau prime for any Z belonging to. So we want to take. So basically, we want to show this. We want to take an element of HQC, right? So it will be every element here is actually a homology class uh, of an element in CQ. Okay, sorry, in ZQC. ZQC. Every element here is a homology class of an element in ZQC. So you choose an element here, then this boundary Q plus 1 prime D Q Z equal to so because just see, let me just write it. This equal to dq minus 1 boundary q z equal to tau q z minus tau q prime z, right? This implies what? This implies that this is this boundary q plus 1 dq z, because z belongs to this, so boundary q qth boundary map applied over z is 0. This is 0. So this is your tau q z minus tau q prime Z. Okay. This implies what? This implies that tau q z, because this minus this is this, right? It means that they are this and this, they are homologous, right? So they belong to same homology class, because their difference is equal to uh, this, right? This is an element of uh, the q c prime. Okay, so this is an element of the this boundary. So it means we have this. But then what you have, this is what? This is nothing but, so tau q z, its class, right? Because they have so same homology class. It means what? Tau prime q z is, but this means what? Tau star z equal to tau prime star z. Okay, so this proves that they are equal. This completes the proof. Next, we have following definition. A chain contraction of a chain complex C is a homotopy from the identity chain map IC to the zero chain map C of C itself. So a chain contraction is a chain of a chain complex C is a chain homotopy from this identity chain map to zero chain map. So this, so identity chain map, means every element goes to itself, and zero chain map, every element goes to zero. So if there is a chain contraction from, if there is a chain contraction of C, then C is said to be contractible. right? Said to be contractible. Uh, a chain complex, a chain complex is said to be acyclic if this is zero, that is HQC equal to 0 for every Q. Okay. So if its homology group is 0 or trivial 0, then chain complex is called acyclic. So next, there is a corollary to the previous theorem. Corollary. A contractible chain complex X is acyclic. That is, homology group of that chain complex is 0. Proof. Let C be a contractible chain complex. This is a contractible chain complex. Hence, this identity chain map is homotopic to 0 chain map of C by previous theorem because they are homotopic to then the induced homomorphism by them will be equal. This IC star equal to OC0C star. But identity chain, so this homomorphism induced by identity chain map is actually identity homomorphism on C, and 0 this induced by this is the 0 trivial homomorphism. Yes. Hence, this is possible only when a homology group itself is 0, which is possible only if this completes this proof. So every contractible chain complex is acyclic, but converse is not true. So let us see an example. So consider a chain complex C, right? where CQ equal to 0 if Q is not equal to 0, 1, 2. Okay. Other than, so except C0, C1 and C2, other CQs uh, except for Q equal to 0, 1 and 2, CQ is 0. And this C0 is Z, which is C1, this is your C2, C1, and C0 is J2. So we have this chain complex Z going to Z, J2, and this we consider this to be alpha, this one we consider to be beta, and alpha n. Of course, every homomorphism from here to here can be given like this, is 2n beta 2m equal to 0 and beta 2m plus 1 equal to 1. So we can define beta like this. So on even integers, even integers go to 0 under beta, and odd integers go to 1 under beta. So then what will happen, you see that so here of course this is C0 and so here I can see that alpha beta, of course, yeah, we will have 0. So alpha is injective. So you see alpha n goes to 2n. So alpha is injective. So kernel of so Z2 C is 0. Okay. Hence H 0. Of course, S3C and so on, they are 0 because that CQ equal to 0 for Q greater than equal to 3. Now, what is this? So, what is the kernel of this? Z1C equal to, you see, all the even integers, they go to 0. So, it is 2Z and B1C. So, n goes to 2n. So, all the even integers will be covered, right? So, it is again 2Z. So, your H1C is your Z1C quotiented by B1C. So, both are 2Z. So, this is 0. H0C is your see beta is surjective. So Z0C quotiented by B0C. So here kernel is whole Z2, because you see 0 and 1 both are there in the image of beta. It means beta 0 C, sorry, B0 C is whole Z2 0. So you can see that this C is acyclic. Uh, Hence C is acyclic. Uh, but C is not contractible if D is a homotopy from IC to C, right? If it is contractible, then of course there will be a homotopy from here to here. Then what we have, let us see. Then we have here IC minus 0C equal to uh, this D uh, uh, so this is D0 1 plus uh, D minus 1, but this so here basically we have dq boundary q plus 1 plus dq minus 1 boundary q equal to tau q minus tau q prime. So here we want to put actually this and this is 0 2 0 this, but boundary this is actually 0 man, this is actually 0 man, because you have z and then z2 and then 0. This is beta alpha. Okay, so this implies your boundary 1, this is beta, then d naught. So this is 0 equal to identity. Implies d naught is the right inverse of beta. But you see that your beta is from Z to Z2, okay, and uh, so if it has an inverse, then it will be from Z2 to Z, right? But any homomorphism from Z2 to Z is going to be trivial. Any homomorphism from Z2 to Z So any homomorphism from Z2 to Z will have to be trivial, because if 1 goes to some n not equal to 0, then 1 plus 1 will have to go to n plus n. But 1 plus 1 here, it is going to be 0. But 0 will have to go to 0. But here n plus n cannot be 0. So, this is a contradiction. So uh, this implies that uh, there is but this is not possible. This is not possible because every homomorphism from Z2 to Z is trivial. So this completes the verification that converse of the fact that contractual chain complex the contractual chain complex is acyclic, so its converse is not true. So, but there is a theorem which says that a free chain complex is acyclic if and only if it is contractible, if and only if it is contractible. So in general, this is not true, but for free chain complexes, this is true. Free chain complexes means this chain complex is called free if each CQ is free. abelian group. So let us see the proof of it. Uh, so one part is already proved that if C is contractible, then it is acyclic. So here we prove that if C is an acyclic pre-chain complex, then it is contractible. So if this is there, then for each Q, uh, for each Q, this boundary map from C plus okay, for each Q, this from C Q to B Q minus 1 C, which is equal to Z Q minus 1 C, is an epimorphism. Epimorphism is surjective homomorphism. So because this chain complex is acyclic, so HQC is 0 for every Q. It means that ZQC quotiented by BQC, this is 0. It means that ZQC equal to BQC, right? So that is why we have it. Now this is a surjective homomorphism or epimorphism, since CQ is 3. So its subgroup if subgroup of a free abelian group is free, so its subgroup ZQC is also D. Minus 1. Same thing. It is free. Now and so hence there is a homomorphism S Q minus 1 from Z Q minus 1 C to CQ which is a right inverse this is a right inverse of so how it is we just see here. You can just see here that because this on the Q from CQ to ZQ minus 1 C, this is surjective. So we can this kernel of so ZQC, we can write this CQ like this. We can write it. In fact, the isomorphic, right? So we can always define, because of this, we can always define a map SQ minus 1 from ZQ minus 1 C to CQ. Just inclusion, right? Because this we can consider a subgroup of this. So this you can see. This is a result. If this is CQ is pre-abelian, right? Then means we can write like this. Now, so you can just consider inclusion. If because of this, you can consider this as subgroup of this. So this map you can consider inclusion map, right? And then when you compose this with this one, right? Then you will get this on the Q SQ minus 1. It will be identity on ZQ minus 1 C. Okay. Okay. Yeah. So it will be this. This is going to be right inverse of this, because basically if you take an element here, then x y will be of the form x y, or x is here, y is here, right? And if you take y here, then you can define a map which is something like y goes to 0 comma y, right? And if you apply this on the Q, so this is your SQ minus 1 from the Q, this is 0 plus y, okay, this is y. So this compose, this is just identity, y equals to y. Now, ICQ identity map on CQ minus SQ minus 1 C boundary Q this maps Uh, so if you take an element here, then if you apply this, then you will have an element here, and take an element here and you apply this boundary map, then you will get an element here. So it is something like x comma y goes to, when you apply this, you will get y, okay, uh, 0 comma y, and when you apply sq minus 1, then it is again 0 comma y. And when you come this subtract for this from identity map ICQ, then of course this is an element of yeah. So this is a map from basically CQ to ZQ minus 1 C identity. No. Okay, it takes CQ to ZQ minus C, then it takes ZQ minus C to this. So, oh yes. And I see you, so xy goes to xy. Okay. So this is, yes, this is actually ZQC, because you see that one map, this map is this, this goes to this goes to this, and ICQ is just xy goes to xy. So when you subtract from here to here, then you what you have, xy goes to this minus this. So y will cancel, it is x comma 0. But x comma 0, when you apply boundary map, boundary q, get boundary map over this, you will get 0, 0. You can see here. So it means that this is an element of ZQC. So that is why this is a map from here to here. Now, put dq equal to sq I CQ minus SQ minus 1 boundary Q. So this is a map from CQ to ZQC, and then when you apply SQ, then it is a map from CQ to CQ plus 1. Now, what we have, dq boundary q plus 1 plus q minus 1 dq minus 1 boundary q equal to what we are getting. Let's see. This is equal to what? Boundary q plus 1 dq, we'll just write this as it is. Just q ICQ minus q minus 1 boundary q plus this dq minus 1, that is just q minus 1 ICQ minus 1 minus just q minus 2 q minus 1 and boundary q. Now let us see what is it here. This is because this SQ is right inverse our boundary q plus 1, so this we are going to get this equal to ICQ, this one, and here this is your this is your identity ICQ. So this composed with this is identity ICQ, and this composed with this so here this is so SQ so this composed with this will give identity map, and then this will keep this one as it is, and then boundary map applied and this something should cancel also. SQ minus 1 boundary q, this will cancel with this, then SQ then boundary q minus 1, these two will cancel, so this will give this and this so SQ minus 1 boundary q, so this give identity, and then this and then this and this, that they will cancel, and now only this term is left. This is going to give this. So ultimately we'll get this itself. So this is nothing but equal to ICQ minus UCQ, right? Hence ICQ, this is homotopic to this completes the proof.